All right, everyone. Welcome once again to another one of Mr. Martin's math videos for British Columbia Math 9. We are on Chapter 5, looking at linear graphs. And today specifically, we're going to be looking at interpreting graphs. So by the end of this lesson, you should be able to describe patterns and trends for a given linear graphs, estimate values between known values, and extend graphs to estimate values beyond known values on the graph. All right. So it's important to be able to study a graph and interpret some of the data the graph seems to be communicating. After all, the purpose of a graph is to display data in a visually appealing manner so that the patterns and behaviors intrinsic in the data become more obvious and easier to notice. Today we're going to be studying some graphs trying to understand some of the behavior the graphs seem to be trying to tell us. First, let's have some fun by looking at some interesting correlations between two sets of data. Before we look at these, obviously, right now, is COVID-19, and every day we're bombarded with, cases and flattening the curve, so a lot of you guys are, I'm really, there's a lot of really great learning, and experiences right now with all the graphs that are being communicated to you with COVID-19. Though it's a terrible situation, we do have, it does emphasize the importance of graphs and how to read graphs and understand graphs. We see what happens when, people don't know how to understand data and graphs and those kinds of things. They take out their signs and they take off their masks and they go, protest. that's kind of what happens when you don't know how to read graph. You've been warned. And so it's important to be able to know how to read a graph. Okay, so let's take a look at some of these, see these graphs lines and how they go together. So on this graph here, we see the per capita consumption of cheese in the U.S. and the number of people who died by becoming tangled in their bed sheets. Okay, so we see here, so there seems to be this trend between the two, that the graphs kind of move together. So do we actually think then that the amount of cheese a person consumes has a positive correlation, has an effect, a direct effect on how many people die from becoming tangled in their bed sheets? Hopefully the answer to that question is no. There's always this thing that they talk about in data science. They'll say correlation is not causation. If you do enough data mining, eventually you'll find lines that kind of move together. There's matching high points and low points, but that doesn't mean that the two things that are being graphed have anything to do with each other. Okay, they just mean that they just happen to have these, similar dips and tops to them. Okay, but there's no logical reason why the amount of cheese a person eats would affect their likelihood of dying by becoming tangled in their bed sheets. Similar to this one here, divorce rates in Maine, and also the per capita consumption of margarine. Okay, so it turns out that if you want to have a happy marriage, you need to, according to this graph, reduce your margarine consumption, right? Because you see that they both kind of dip very similar to each other, right? So all these self-help books that tell you, 5 steps of having a happy marriage, blah, blah, blah. No. All you need to do is cut margarine out of your life. That's all you need. Just kidding. Obviously, this is another example of how lines can move together, but for completely random reasons and not actually one causing the change in the other. Okay, but this is, something that people using graphs and data do all the time, right? And so it's important to kind of understand how to read graphs, how to make sense of them, and that's what we're going to be trying to dive deeper into today. So Let's take a look at an example. So for example number 1, we're going to solve a problem using interpolation. Ooh, big fancy word. We're going to talk about what that word means in a second here. So, but first let's look at the problem. A weather balloon recorded the air temperature at different altitudes. The data approximately represents a linear relationship. Okay, so here, the altitude you're at and the temperature. Do you think the altitude you're at above the Earth has an impact on the temperature, or are these two randomly matched numbers like these two previous graphs? Well, hopefully your answer is no, they're not randomly matched. The higher you are, the colder it is, right? That's why the tops of mountains have snow on them, right? The bottom, you never have a mountain with just snow on the bottom half and nothing on the top half, unless it's volcanic or something and it's in the middle of an eruption. And so these are obviously, going to move together. Okay, it turns out they actually move together in a straight line, a linear relationship, which means they have a constant rate of change, if you guys remember that word from last set of notes. Okay, so at the altitude of 350, you have a temperature of 11.4 degrees. Okay, that's cool, but it's not crazy cold. All right, put a little jacket on, you'll be all right. But once you get to like 1,500 meters above, I'm assuming sea level here, you're at negative 5 degrees Celsius, and you go another 300 meters, you've doubled the temperature at negative 10 degrees Celsius. And so some real differences here when it comes to temperature and kind of what you experience based on how high you are. And this is the graph we have here, right? Air temperature, and this red line here represents the points that we have on the table. Okay, if we were to actually map some of these out here, the first one was 350, so 300 is here, 350 is here, and it had a temperature of 11.4, right? And so it gets us our first point. Second point was 750, so this is 750, gets us 5.7, right? So just a little bit. So you see how the points kind of find their way to where they are, okay, in this graph. All right. So the question A asks us to interpolate the approximate value of the air temperature when the balloon has a height of 600 meters above sea level. Okay. So first we got to figure out what interpolate means. So let's put a definition to the word interpolate. To interpolate is to calculate or estimate a value between two known values. Okay? So calculate or estimate a value between two known values. Because here's the thing. This graph is very presumptuous in some ways. Okay? Because here they're telling you, okay, I have a data point here, 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 and here, based on the table we have, right? We don't have any data between here and here, or here and here, right? We don't have data for like 800 meters. We don't know. But here, the artists were so bold to connect the dots with a solid line. And by doing that, they're making an assumption. Okay? And I know it's a fairly reasonable assumption, but it's an assumption saying that between the points that we've plotted, the temperature and the altitude will continue moving together in a similar way as, the trend of the dots that we have plotted would indicate. Okay? Those lines, though, those are assumptions. All right? But I think you can agree that they're a reasonable assumption. Okay? So here we're going to look at the temperature for 600 meters. So first thing I got to do is find 600 meters. There it is. Someone's already traced a nice red line here for me. I'm going to get rid of my... Okay. Someone's traced a nice red line here for me. Well, I'll trace it again in blue highlighter. So you can see at 600, I'm about halfway between 5 and 10. Okay. So how you're seeing is that you're going up from the altitude, okay, and until you hit the line that was traced between your known points. Once you hit that line, you turn towards the other axis to get the temperature in this case. Okay, so once I go up and hit this line, then I turn towards the other axis to figure out an estimation of the temperature. So here, what would you say the temperature is? Halfway between 5 and 10. I'd say about 7.5 degrees Celsius, right? 7.5 degrees Celsius. Awesome. So let's try a different one. What is the approximate altitude for a balloon with an air temperature of -7 degrees Celsius? Okay, so in this situation, they're not giving us the altitude. They want us to solve for the altitude. Okay. So we're starting from a different axis. We're starting from our temperature axis, which is the y-axis, and finding the corresponding point on the x-axis for where that line is. Okay, so again, I start 7.5, halfway between 5 and 10, -5 and -10, so that's -7.5. I start moving towards the line. Once I hit the line, I turn towards the other axis, and it gives me an estimation. It's just over 600 meters. I'll say 1,600 meters. I'll say probably about 1,630 meters. That's my guess. Okay, definitely a bit of an estimation there. These tables go up by 200, and so it's hard to know exactly what's in between each of those lines. All right. So C, is it possible to interpolate the precise value for the air temperature when the altitude is exactly 1,550.292 meters? What do you think? Yes or no? I can hear you. Just say yes or no. The answer here is no, right? And why would that be, do you think? It's because the graph lacks precision. Okay? Graph lacks precision. Specifically these kind of grid lines. Okay? If we had more grid lines, it would be even more precise, right? If it had even more grid lines, I could maybe go up by 50s instead of 200s. But even then, I wouldn't be at the same precision as they're asking for here. They're not going up by 50s. They're going up by 0.01 of a meter, or 1 centimeter to be exact. And so I would need a very, very thinly drawn line to be able to get a precise value. So, but I can get a nice estimate, which is most of the time what we're looking at when we're looking at graphs. It's all about those estimation skills that we were talking about at the beginning of the year. So that's what we want to use. Okay, let's try another one here. All right, but now instead of interpolation, we're gonna learn about the sibling of interpolation, extrapolation. Okay, so we're gonna solve this problem using extrapolation. So Anna is kayaking up the east coast of the Queen Charlotte Island towards Graham Island. Queen Charlotte Island towards Graham Island. Here it's beautiful country up there. So Anna's course is shown by the arrow on the map. So this is Anna right here. Okay, Anna's kayak started here. All right, she's rowing, right? She's got her little, okay, and she is heading towards Graham Island. Awesome. So, if Anna continues on her present course, extrapolate, there's that word again. Oop, nope, don't mean to cross that out. Need to highlight it. The values of the coordinates for the latitude and longitude where she will land on the island. Okay. So first let's define extrapolate, right? We can't extrapolate without knowing what it means. All right, so to extrapolate is to estimate a value by extending a pattern, in this case a line, beyond what is known. Okay, so here, to extrapolate this line, okay, so we know that Anna is heading here and she's already traveled to here, right? But if I want to know where she's going to land, assuming that, and again, it's important to say this, again, this is an assumption, right? We're assuming that Anna's direction is going to stay constant, okay? Assuming that her direction is going to stay constant, okay, I would say that she's going to land somewhere there, where that red dot is, okay? But that's an assumption. Is Anna necessarily going to end up exactly there? No, right? She's likely to. We can say that, and we can estimate that, but there's no guarantee. Maybe like there's a Russian submarine or something that's going to interrupt her path here. Maybe there's some orcas that are going to cause her to change directions. Okay, I'd be freaked out if I was in a kayak by myself, surrounded by orcas. Those are their fins. Don't judge. And maybe there's a big whirlpool here, right? That's gonna cause her trajectory to kind of pull inwards, right? There's all kinds of nonsense that we can talk about here in terms of what could make it so that Anna's trajectory changes. But assuming that all of these scenarios are unlikely or irrelevant, I can make an estimation that as nothing else changes, she would land approximately here. Okay, and then I can find the value of that point. Okay, this is if this is a half, I could say maybe that's 553. This would be 0.75, 0.5, 0.25 between, right? So, I could say maybe 53.75 degrees, and if this is, I'll use another, kind of 0.75, 0.5, 0.25 between, and then negative 1.75 degrees. Okay, that would be kind of my rough estimate. Again, there's not enough grid lines on my graph to come up with an exact answer. That was a problem in the last question. But yeah, so could you use extrapolation to estimate where Anna sailed from? Yes, we could. Okay, it would be an assumption that we're making that the line is not going to change directions. Okay, it's like someone looking at an investment. Oh, that Tesla stock looks so good. It's just going up and up and up. And I'm going to guess that it's going to keep going up and up and up. So I'm going to buy it because I want to make a return on my investment. And then you buy it, and then the line changes directions. Like, what happened? The markets are supposed to be efficient. But expectations can change based on, unexpected events like COVID-19. So we can extrapolate beyond a known line. But again, those are some assumptions. Which assumption, though, do you think safer to make? To interpolate between two known points, or to extrapolate beyond the last known point? Which is the safer assumption? Hopefully you answered interpolation. That is, the majority of the time, that is definitely the safer assumption of the two. Okay? Because less things can go wrong between this point and this point than, this point to infinity, right? So relative room for error is very small because the points are close to each other on the graph. Okay? So that's the notes for today. Hopefully by now you are able to describe patterns and trends in a linear line, that you can estimate values between known values, so that would be the interpolation piece, and that you can extend graphs to estimate values beyond the known point. That would be the extrapolation piece. Okay, your assignment is here, and it'll be due on Wednesday to be handed in on Teams. All right, and I'll see you guys next class. Goodbye.